So, good morning, everybody. This will be the 7th week of the problem solving session for Mechatronics. And this week, unlike the last weeks, we'll be covering 2 weeks of classes because we want to solve questions in these classes, and week 7 and week 8 both have a dearth of many problems, actually specific problems. There's plenty of theory and lots of very interesting concepts that I highly recommend you go through the lectures. But we'll be solving questions in this class, and therefore we'll focus mainly on we'll be covering both week 7 and week 8 lectures. Are there any specific questions you have about these 2 weeks? Yes, Rakshit?
So you'll be talking about the quadruple robot, right?
Yeah, we'll go through the lectures for that
Sorry.
because I didn't write the things in that, but yeah.
Okay, that's all.
Okay. So in lectures 31 and 32, we talked about controllers and digital controllers. And if you notice, a lot of things we have done in these two classes were things we had already done before. Like essentially, PID controllers can be written in can be properly done in terms of a PID in terms of using operational amplifiers and the like. And PID controllers are incredibly useful. For example, for one project we had done, we had a beam and a ball on this beam. We have placed a ultrasonic sensor here and a motor here, so that we can control the angle of the beam. Using a simple PID control of the input of the PID control is this distance, and the output of the PID control is this angle, and provided you tune the Kp, Ki and Kd values, this can actually become a stable system. So even though a PID controller is so simple in principle, it is still incredibly powerful in its capacities. So we'll solve a couple of questions based on the block diagrams, and okay, not a couple of questions, one or two questions. And then we talked about and then lecture 32 talked about the digital counterparts to controllers, and essentially the only major difference is the addition of ADCs and ADCs and DACs. Lectures 33 talked about program logic controllers. There are a lot of definitions and components to this, and we'll spend a huge chunk of the class looking at these questions about drawing ladder diagrams and the like. For that, I will send a link in the link in the Google Meet, and then you can work out the questions as I'm doing it here. Lectures 34 and 35 talked about inputs, outputs, communication, and lectures 35 talked about fault finding, and those did not have any specific questions. I mean, there were one or two questions based on bit rate and baud rate and those things, but those are essentially plug and chug questions, and you can solve them yourself. We have enough practice solving plug and chug questions. That concludes week 7. In week 8, lectures 36 and 37 talked about lectures 37 and 36 and 37, we had questions about we didn't have questions. We had proper mechatronic systems, and it's essentially a culmination of everything we have done so far. So lecture 37 had the myoelectric controlled motor, and lectures 36 had it had the wheeled robot with it. Essentially showed you how to use 80 mega for on a wheeled robot. there isn't many problems in that. Essentially, you can go through it and understand how actually we use microcontrollers and things like that. Lectures 38 and 39 talked about the ABU Robocon, which the prof taking the course was very involved in. Once again, I will not be specific. There are no questions in that thing I can solve. And finally, lecture 40, we talk about legged robots. Is there any specific question? Is there any specific question you have about the legged robots?
No, just go over like an overview on it. If I have any doubts, I'll tell.
Okay, fine. So we'll first start with a simple block diagram question. Is the question visible? Uh, I'll give 1 minute to solve this. So when solving things about block diagrams, I make it a habit to mark each signal properly. So why is the signal output here? So why is the signal input to M? That means that this signal here in this wire will be My. This is one of the main reasons we looked into transfer functions, because in reality, if you are writing this in terms of time, it's some weird expression in time. But because if you're using transfer functions, we saw that for transfer function it's just a product. Now, this signal here will be will be the output of this, so it will be X minus My, because we are adding the input X and subtracting the input My. This, for clarity, I'll just write this as E0, this is E1, this is E2, and this is Y. Now we have E0 is equal to X minus My, E1 is equal to G into X minus G My, E2 is Gx minus Gmy plus D. Y, because Y is the output of this after H, is H multiplied by E2. Okay, so okay, wait. We can take the Y to the other side, and thus we get therefore the final result is okay. So So this is the in general this is the steps you do when you're solving block questions with block diagrams. Specifically, if you have a closed loop, you can naturally make these kind of questions even more complicated. For example, a question which involves position control is essentially, since motors usually allow for very nice velocity control, if you're going to do position control, you need an integration of the velocity, and therefore you'll have loops of controllers. For example, we'll have integration was S or 1 by S. I think integration is 1 by S. Yeah. Like, you can have massive systems, but the way to solve these will be almost the same. So we give a input of position. This is essentially a differentiator. Sorry, an integrator. Sorry, the 1 by S is here, and the S is here. So we give the position here, theta. Taking the derivative of the position, which is essentially a multiplication by S, will give you the required angular velocity, and we have a closed loop system inside to specify to get the specific angular velocity, and then we can integrate it again to get the actual position and subtract to get the things and so on. So essentially, once you get understand the premise of how to get the closed loop, how to write the y as a once this makes sense, how you get y in terms of x and perhaps in terms of any disturbances, you can write this easily for higher order terms. So that's essentially that's all there is to controllers, block diagrams, and open loop and closed loop systems. For open loop systems, the thing is practically trivial. We just have x, g, h. So if we take this, copy, and we remove the feedback, then it's practically trivial. So we have E0 is equal to x, E1 is equal to gx, E2 is equal to gx plus d, and y is equal to hgx plus ht. So open loop systems are fairly trivial. Now we'll move to the part in PLC. For PLC, I will send you everyone a link in the chat. Like, in the end, the best ways to understand how the PLC systems work is by, well, programming it out yourself. So this is how it might look for you. Because my screen is slightly smaller, it might some parts might look different. I hope everyone can see the app. Okay, so if you want, you can check out their conveyor simulator, but I was thinking we'll go through some of the things we have done in class first. So most of this not signals, the symbols here have the same representation as we had in class, except that because this is made by a specific individual, some of the things are not standard in my opinion. So for example, let's have a we'll first make a couple of variables. Let's say we have a variable called start, which is a boolean, and we have a variable called stop, which is also a boolean. Yeah. So here we can add a okay we say so we'll just have a very, very simple one initially. So given an input to start, we'll change the value of stop. Super easy. So if you start this, naturally, because since start is false in the beginning, this rung of the ladder will not run. But if I click this, I've set start to true, and that changes stop. I can now set start to false again, and that makes stop back to false. This is kind of intuitive in my opinion. Are there any questions about this? We can move on to more complicated concepts in a while. So for example, let's introduce a motor. This variable will tell you if a motor is switched on or not. Now naturally, in case you're not able to select the thing, you're probably in simulation mode. Oh, do I have to explain the interface? I think I should. Okay, so you can completely ignore this region. That's for saving and storing the values. The undo button is perhaps useful. The question mark will take you to a video link, and sharing is essentially sharing the concepts, sharing the specific ladder you have to run. These are for the simulation and editing the elements of the ladder. So say I have put a start here. Now right now I've selected the stop. I'll use the mouse. Right now I've selected the stop. So because of that, and there's only two things in this rung, so I can only move left. So if I press the left here, I would have gone to start. Because this is right now a picture, I can't show it to you. And if I click the green arrow, it naturally means to simulate. Then these are many of the components we have. The last one adds a new rung to the ladder. This one splits the ladder into two. We'll see that in a while. You can ignore these three for a while. This one is an input. I mean, it checks whether a particular thing is on a boolean, and this is to set a particular thing, set a boolean value. And this is a delay, which we have mentioned in class, and this is a counter. The other three are also kind of mentioned in class. So here, these are the variables we can use. There are many kinds of variable: boolean, counters, timers, integers, and so on. And the main region is where you add the ladders. Now I'll close this. So I said earlier, if I press left here, it will take me to start. Oh, it doesn't take me to that. It moves the thing to the stars. It switches the order. So say I have a couple of inputs. If, as you notice, as I'm pressing all the inputs, it will be to the left of the thing. And now if I want to reorder them, I'll just press the left here to move them accordingly. Now if I add a new rung, I added a new rung. Now you can reorder the rungs up and down. You're using these. I don't need these many inputs. And so say I've selected that. This gives you an option to make the split thingy. So say I want to. Okay, so one of the first things we had done in class was to make a latch. So for a latch, what we had done was, at the end we want the motor to be moving, and essentially whenever we only want to press the start button once, and after it's so if we had so if you're I can delete this, give me a second, delete. So in general, for the motor, we usually will have like a start and a stop. Now how will we incorporate a stop here? So one logical way could have been to have a include on this thing, and this one will be a normally closed. So if start is true, if start for the motor to run, we need start to be true and stop to be false. So that's the way. Yeah, right now you can look at the values in the terminal, I guess. So right now everything is false. If start is true, the motor switches on. If stop is false, if start is true and stop is true, I am so sorry. Here start is true, but because stop is true, nothing's happening. One of the first things sir had shown in class was to make a latch. Like, say we had another rung, and in this rung, so we put a start, small delay, so these are the different things. I'm making start delay as a timer. Here I'll set the values. So first, oh, I forgot things. So if PT is present time, this should be, give me a second. So yeah, so as you see, PT shows PT is the maximum time the timer will stay will be on for. ET is the present is the time at which it starts. So right now start delay is false. Sorry, start delay is not start delay as a timer is not switched on. So but that's why ET is 0. Now when I start, I will first set start to false. Since start is not true yet, start delay doesn't start, obviously. So when I switch this on, you can see the timer starts increasing. I'll increase the timer length to show it better. So as you see, the timer length is slowly increasing, and after it's done, the rest of the thing will work. So what I want to do now is, every time I switch on start, I want start to be set to 0 again. Yeah, So every time I switch on start, it will be after a after a min after a after 10 I don't know how many seconds that is, but after some time it will be set to false again. So now I mean that's this is how it sometimes happens. And if this is the case, how do I make the motor work as I wanted to? I can set this okay. So now here we can use the proper latch mechanism. So here I'll add a new this thing. I'll delete that. I'll make us put yes. And here I put so this was the latch mechanism as shown in the class also. So now say I switch on the thing. Start is back to false, but the motor is still running because the input from the motor is still true. So now the only way to make this only way to stop this is by making stop making stop giving an input of true for stopping. So now everything is switched off. Naturally, if I do this, even switching on start won't make a difference. If you have kept this in stop mode, obviously there's no point in switching on start. But yeah, so this is how to make a latch. So you guys can play around. One thing I would have you try to do is try to make make two rungs which will alternate. That is, the first ring should keep going for like 1 minute. Sorry, 10 seconds. And after that, the second ring should go for another 5 seconds, and then it should just keep alternating. So I'll give you like 5 minutes to do that. So I'll write that question. By the way, if anyone has joined newly, how will I share the link all the time? So anyone joined newly, this is the thing I'm using right now. You can use it to check out PLC coding. So did you guys work it out? Okay, so just delete. So first we'll first have two variables for the two rungs. Rung 1, and that is boolean. Rung 2, which is a boolean. We'll have starts and stop again. We need two delays. So time 1, which is a timer, and time 2, which is a timer. Okay, so first I'll just make the thing. I'll have another timer for. I'll just have another start reset. So I'll just first make the reset thing for the start. So every time we press start, after a short while it will set start back to false. So essentially, if every time I press start, every time start is false for a brief moment. So now we'll just add two rungs, and these are the rungs which will alternate. So we'll first do the latch thing. So this is the first rung essentially, and we want it to work whenever rung 1 is on. We put a small up. We'll set the timer. So let the first timer be for 2000, and the second one be for 2000. And after that we have to set rung 2 to true and set reset rung 1. Likewise, rung 1, and here we. So essentially what will happen is, okay, so whenever we press start, this just worked. Oh, oh yeah, what we need is We need another rung. That's not what I want. Here, time1.in, yeah. What is going on? Rung 1 should be false. Okay. Time1.in. I'm very sorry about this. Okay, so one way this could have worked out much better was, say rung 1 is already true, then this would work. So now half the time the first timer is you can see that right now this timer is running, now this timer is running, and then this timer is running, and so on. I was just trying to get away with having to. I didn't want to start with rung 1 being true. And you can even look at the variables. So here rung 1 is false, and shortly after it becomes true, and so on. I can stop this by just pressing stop. Now nothing's happening. Even if I do press start, nothing happens. If I let go of the stop, it works again. So that is a small disaster, but yeah, we can do similar questions like that, like in the. In addition to these, we can also include a counter. So say I can place a counter here. Okay, let me just make a new counter variable, counter 1, and that's a counter. Submit. So now what will happen is, as this is running, the counter will slowly increase, very slowly. What's happening? Wait, oh, sorry. Oh my god. Yeah, the program is glitching. I'm very sorry. Like right now it should have set this to false before it moved on to here, but it's not doing that. Yeah, so for I mean, essentially the I believe I'm actually right, because this region here should not be green right now. Right now, rung 2 is false. Rung 2 is a reset. That means this entire region has to be black, because it's not being. It shouldn't be running right now. But because this region is accidentally being run and it's set as rung 1 is set as true, the program is get wondering whether to reset rung 1 or to set rung 1, and therefore it's at a impasse. But yeah, that's the premise behind a PLC. This could have gone a lot better if, yeah, you can. I can remove this here, add that here. So it's working properly now, and I'm not sure why. Okay, doesn't matter. So now I can just press start, and the counter will increase again and again. I can set the counter to reduce instead, and now if I run, the counter will is slowly reducing. You can see that. Oh, I get it. The counter is not giving a weird output, and therefore it's making things weird. Okay, it doesn't matter. So that's the premise of the PLC programming. I hope that. Is my screen visible? Is my screen visible?
Yes, yes.
Okay, because in my the recording software it showed was not visible. Okay, okay, that scared me for a while. Okay, so that will kind of conclude the PLC thing. Also, do you have any specific questions? So after this, I was planning to go through Sir's lecture slides for the different week 8 stuff, because many of the programs are essentially, I mean, yeah, where did the program, yeah, so these kind of stuff you can only be done with the actual equipment and stuff, because even if you see the code on the computer, I can't run it right now because I don't have this many of these microcontrollers right now. Like a few weeks back, I had shown how to write Arduino code, and this one is slightly different. So in Arduino, the Arduino's one which I had used, we had specific control about which pin to change and things like that. But even in the Arduino one, only certain pins can be used as an analog input, and certain pins can be used as digital input and things like that. And that is similar in these cases. To be frank, I feel like this syntax is a lot more cool in my opinion, because it looks like you're actually programming with very fancy terms. Oh, by the way, so once again, these are stuff we had learned in the previous classes, like converting in binary and hexadecimal and things like that. So instead of writing OB00001111, we could have instead written 0F, OX0F. Wait, sorry. Hexadecimal is 2 to the power 4. Yeah, it will be we can instead of writing OB00011111, you could have technically written DDRA is equal to OX0F. It will have the same effect. and I think all of these kind of make intuitive sense. Here you're defining the this is written in a C type C kind language, language like C. So when you're doing this, you're first defining the frequency. You're including the packages which are used here, like slash delay ms is probably from the util delay.h. Here we are defining what the outputs and inputs are. Here you're saying your these specific LEDs are glow LED connected. Yeah, your specifically glowing LED PB3 and PB4. Why is it that one? Yeah, so I feel like to make perfect sense of why this is happening, we need to look at how the connections are. I mean, how the LEDs are connected. But yeah, so all of these are essentially the programming methods. I felt like the end of this. Like this is a prime example of what one example of what a mechatronic system can do. So as you see, this we have the we have a proper system where there are sensor readings, there are actuator outputs and things like that, and even a little bit of data manipulation. A little bit of data manipulation to understand, and the data manipulation is done through the program. Essentially, you read the data, and according to the specific data, the output of the motors are given. Yes, Harichandran?
Yeah, in this short lesson, it was very clear. This example, this robot operations.
Yeah.
Uh, so this, I think, these are the parts are commercially. Is it available?
Yeah, many of these things are commercially available. I'm pretty sure all of these are commercially available. For example, essentially all you have for this are where, yeah, IR sensors are commercially available. 80
Uh,
mega is all definitely commercially available. It's the 80 mega is not very cheap, but you can get it. The like what did we use? We used Arduino Mini.
You
Arduino,
know.
yeah, yeah. We used
Uno,
Arduino. We used
Uno.
we actually used a smaller version. I'm pretty sure there's a smaller version to Arduino. Give me a second. Arduino. Yeah.
It's Uno, I
The,
believe.
yeah, that Uno is there, but we have also sometimes used Arduino Mini because we don't many sometimes you don't need all the pins of Arduino, so we can
No.
we had used Mini once or twice
Yeah,
to
it's pretty similar. Just the
yeah,
even the
yeah.
coding part is very similar.
It's similar. I'm just saying that we can. Some of them are cheaper. That's why.
Okay, can we get this end of the session? This bill of material, so we can try this with the market, and we can try it.
I have a small question. Is my screen disappear? Screen getting blank now and then?
No, here it was very clear.
In that, because it is getting blank inside my what's that thing called in the screen recording, and that might pose a problem. Can you give me a Okay, we'll take a short break here. I will fix it and come back.
Yeah. Thank
Don't worry, I'm still here. I'll just fix the camera. Yeah. Okay. I'm back. Hello. Am I audible?
Yeah, it's
Okay.
clear.
Okay.
So what I am requesting, can we get that bill of material for uh, this RoboKit experimental? So I can try this.
The Robo Kit. I mean, you're talking this one, right?
Yes, 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 same.
The thing is, for this specific one, I am not sure where to get the pin wire and chassis. Like everything else is properly available. I mean, pin wise. I mean, the jumper wise you can get, but I'm not sure where to get a specific chassis from. Yes, Rakshit.
So I would recommend looking it up online. But if you're living near Bangalore, that's what you might find all the components. I would
Yeah,
recommend doing it in Arduino than using.
yeah. I also personally prefer Arduino because I find Arduino programming a lot easier and more intuitive. Because even though this looks pretty cool from a programming perspective, in the end it's much easier to specify which pin is out. For example, in Arduino, all you have to do is literally pin dot. Sorry, it's much more easy than whatever this is. So yeah, I also would recommend Arduino. And technically speaking, you don't have to specifically do this. You can do a
No, it is not like that. Basically, this one. At least we try with the experimental with the one thing. We will get it know that how the this system was interconnecting with the others
okay.
and
in that case, what I would recommend is you can buy the following thing. You get a microcontroller like Arduino 80 mega. Then you definitely need jumper wires.
Yeah.
Okay, get a breadboard uh, and a couple of sensors, like perhaps a potentiometer and
Ultrasonic also.
yeah, ultrasonic is very useful. And what's one more which I forgot. And then a servo motor, and a couple of LEDs. A servo motor is fun because essentially the output of a servo motor is the angle, and therefore you can like properly tell the like one experiment I had done. I think the experiment I showed you was we changed the value of the potentiometer, and by changing the value of the potentiometer, the servo will move the same angle. It's a very small thing, but it shows how these things work. So
Yeah, that's we can do that some hands-on experience.
yeah, and then after that you can you can swap out the potentiometer to the ultrasonic, and then depending on how far away the ultrasonic thing, how far away the objects are from the ultrasonic sensor, the sensor can move. So one experiment you can try doing is like having a door locker. I mean, something which locks a door depending on your proximity to it. So, provided you're close enough, I mean, if once you get close enough, the door will be unlocked, and you can very easily see how the program will work for that. So, essentially, you'll just have if the result from the ultrasonic sensor is less than a specific value, then the servo should rotate a particular angle. So, provided you have the basic components, it's very easy to start up with this.
Okay.
So
After
this
can you
so
give the some guidelines? This material list. So some guideline.
so I guess I can just write it down in the slide.
Okay. Yeah, that's good. Fine.
Yeah. So things you absolutely need. Why is the okay? Why? Okay.
Can also get the Bluetooth module also. That's one of the important things.
Yeah. So in another thing we had used. Oh, I forgot the name. ESP32. So if you use okay, I'll write it down. So there are several microcontrollers out there with many things you can do. So I don't believe the basic Arduino has Wi-Fi capacities. There are Arduino things with Bluetooth. So if you select the ones with Bluetooth, you can essentially make a phone application which can connect to the Arduino and command it like that. ESP32 has Wi-Fi capacities. So what you can do is you can host a server on ESP32 and then connect to that server through a phone or computer, and therefore command the ESP32 to do things with it. And then you need sensors like potentiometer, ultrasonic sensor. What other sensors are would be nice?
Like in this class, this remote, the battery operated. It was showing the switch operated. Whether we can go with the remotely operated remote sensors.
IR
Yeah.
sensor. Having yes.
Yeah, yeah. Yeah, well, but yeah, you can. In the end, yeah, but in the end, technically speaking, it's up depending on what you want to do, right? So, and
Yeah,
no, I'll be honest. Many of these are actually incredibly cheap. The ultrasonic sensor is barely 200 rupees. I think it's much less than 200 rupees. And potentiometer is, I've seen a potentiometer for 5 rupees. Uh, j- Getting jumper wires and breadboards is kind of nice because jumper wires and breadboards allow you to connect these things very conveniently. But some jumper wires are slightly expensive, so like you, that's the thing. Then there are actuators, servo motor, DC motor. Now you can get plenty of LEDs because we can basically use LEDs to debug mistakes and so on. And what else do we need?
that
Yeah, I think that's all. That's essentially all we need.
what I'm asking, that battery actuation we can do that remotely.
Which actuation?
Battery on off actuation, that switching operation we can use as a battery will be actuated by remote with IR sensor.
A battery cannot be actuated.
No, battery on off control, because in this project the manually the switch on the battery when we are seeing this.
Which one are you talking about?
uh, in the video if you see that when the this robo kit was operated manually, switch on that battery kit, then it was actuating.
Oh, I mean, so technically, if you use the correct microcontroller, you can use a microcontroller which has a which can connect to Wi-Fi, I guess. And
Yeah,
if it can connect to Wi-Fi, you can start this up with the with the Wi-Fi signal. Like, give me a second. I will. Can I? Oh, I have to. Okay. Yeah. I will. So, for example, I will now stop sharing the screen and start share. So, this is an old code which I had written. Essentially, in this code, I use an ESP32 microcontroller. The ESP32 will host a web page, and after it hosts a web page, we go inside the web page and we can select the slider, the angle value. And on selecting the angle value using a slider, you'll be able to oh, it's not clear. Okay, doesn't matter. So on selecting the angle value using a slider, you will change the value of the servo. So for we first initialize some very basic stuff, like for example the Wi-Fi name and password. So in my case it was my name, and I put up I mean essentially this is the password, Wi-Fi name and password of my wireless hotspot, or maybe or any Wi-Fi. These are, I connected my server to my the pin 18, and this is essentially telling that I'll be I'll be making a Wi-Fi server. So first, by the way, this is the baud rate that we had seen before in the one of the classes. So first there's a little bit of boilerplate code that you're expected to do right before everything. So from the motor which I use had a frequency of signal of 50 hertz, and therefore I said that. Then I said the 500 and 2500 depends on the duty cycle of the motor. So for if you are if when you buy a specific servo motor, it will have a specific name. Like the one we had used was, I had forgotten the name. Doesn't matter. So when you Google that name, you'll be given the data sheet, and from the data sheet you can figure out which what these numbers should be. So once it connects to the Wi-Fi, I wait I wait for a while until I connect the Wi-Fi. So this is the setup loop. The setup function. So whenever we switch on the ESP32, the first thing that happens is it connects to the Wi-Fi. So and the setup will only complete after it's connected to the Wi-Fi. After it connected to the Wi-Fi, I first defined two useful functions. One function is to get the angle from the request. That is, whenever I say a phone has connected to my to the server, and I'm changing the angle in the phone. Once I've changed the angle, that becomes a request. So the server gets this request from my phone. So the request will be in the form of the string, and I'll essentially read the request and identify the location of the number. So that's what I've done here. So essentially, by reading through the text of the request, I identified where the request is, where the number is, and then I converted that number to the angle using the toInt function, and then I returned that angle. Then, given the angle, I made a function that I made the servo move that angle. So that is the. Then we have a little bit of boilerplate code as I was saying before. So the loop so this checks if there's a client in the loop. Sorry, if there's a for ESP32, the setup function is run once and loop is run continuously after that. So first it checks if the server is available. If the server is available, then it goes into the inner loop, inner if statement, and then it waits until it checks if a client has connected. If a client has connected, that means this one person who has logged in to open the IP address of the ESP32 using the phone or something, and the moment you open the IP address of the ESP32 via the phone, you'll see this web page. We can actually see this web page right now. You only copy 3 lines. So essentially, when you switch on the server, you'll see this. I mean, when you open, when you put in the IP address of the ESP32, you'll see this, and then I can change the angle here. And once if I make the angle release when I click sub, I shouldn't have clicked submit, but yeah. Once I so when you're doing it on the phone, naturally clicking submit won't change anything. I mean, won't change how it looks, but this thing will just take you to a different thing, it seems. So yeah, so whenever you click submit, what happens is a request is sent, and here we read the request. Yeah, so whenever the user clicks submit, you will get a value. We'll get a value from the client, and that is written in. That will be written into the request. And after it's written into the request, we read the. We just put some. We say that yes, we have gotten so and so request, and then we get the angle. We make the thing move, and that's it. So if you have an ESP32, you can kind of like use Wi-Fi and a little bit of code to like control different things. So for example, you can technically make a smart light bulb, as in you can have a light bulb which you can switch off and switch on using your phone. So you can lie down on the bed, and you don't have to go to the plug point to switch on your light bulb. You can just switch it off using your phone. But yeah, there are lots of possibilities you can do. So another thing you can use is you can also include relays in your. I will stop sharing. I guess you can also include relays. But when you're getting relays, you need to know what specific relays you want, because relays, the voltage the voltage and current limits of relays are quite strict. I have unfortunately burnt a couple of relays by not reading that correctly. And please do know that all of these, technically speaking, everything here have very specific voltage and current requirements. So whenever you're using these, you must be careful to not exceed, especially you should not exceed the voltage limits. So yeah, that will kind of that's kind of the premise of this thing, this lecture. Lecture 37, on the other hand, is once again another project. This project is slightly more expensive because the sensors here, I have not used any of these sensors, so I'm not fairly certain, but I pretty sure this is slightly expensive. Essentially, these are projects that you can do given a little bit of money, but implementing these projects will definitely give you a very solid understanding about each of the concepts here. Especially here, the second project is mostly about signal conditioning, which is a very important part about which we have spent a lot of time learning. We learned about low pass and high pass filters for a short while in between, and so on. Yeah. And then there isn't much I have to talk about the Robocon, so we'll move to the design of the four-legged robot. So yeah, as Sir said, four-legged robots are very nice, but the four-legged robot is more in making a four-legged robot and the like is more a mechanical problem. Like everything else we saw more about electronics and computing, but making this, we have to properly write the mathematical equations to know what torque is required and so on. So I'm not certain how prof decided to get how he gets these equations, but do not worry that he did not do this by hand. We can there are programs out there. We can technically write equations and things properly in softwares like Mathematica and MATLAB, and write the equations very intuitively using that. For example, in MATLAB you have the sims command that makes symbolic variables, and you can define a lot of symbolic variables with the different concepts here. Like for example, you can define a theta 1 2, which would be the angle which is what's theta p. Oh, theta p is the angle of the thing. So you can define each of these as specific angles. Say theta 1 2 is this angle, and you can just say theta 1 2 is equal to theta 2 minus theta 1 theta plus theta p. And on doing this, you writing the equations is not that painful. There are a few ways you can write out the equations. You can either do the equations from writing the force equations at every point. Oh, this is theta p. Force equations at every point. Like every link has both has reaction forces from the top and bottom, and a torque equation also. That gives you three equations, and then given the number of links and number of links and the number of, and you have three equations from every link, and that will be enough to solve for all the reaction forces. So here you will have reaction forces from, you have two reactions here, two reactions here, two reactions here, two reactions here, and two reactions here. So that's 6 reaction forces totally, and each of the links will give you 3 3 equations. So this is definitely 1 2 3 4 5 1 2 3 4 5 15 equations. And on the other variables are accelerations and velocities, so you can quite easily solve for these. Okay, not easily, but you can write the equations individually and solve for it. Another way to solve for these equations is by learning a little bit of Lagrangian mechanics, but that's a little off the scope for this. Lagrangian mechanics is nice in the sense that none of the equations are vector. None of the equations are essentially a scalar equation, and then we take the derivative of it, and on taking derivative we get several equations which you can solve for. I think Sir solved this by using the Lagrangian, because the Lagrangian very quickly gives you the torques and torques. So that's how he's probably gotten these values. Yeah, so that is the premise of the last this final lecture. So yes, Harichandran?
Yeah, just to go back, this slide 2605.
56?
No, next that Legatrobo, the photocopy.
Okay.
Next one, I think slide.
The previous one. Previous. Yeah.
This
that one.
Just I need to understand that there is a center one leg was there in the photo.
Give me a second.
Yeah.
Where?
No, in actual photo, there is a center leg was here. This is just supporting.
This one.
center one yeah, the leg. It is just holding this legged robot
This one.
or what? Yeah,
Yeah,
yes,
that's
yes.
just holding a legged robot. Yeah.
Okay, okay. Got it.
Oh, yeah.
So there is a here the previous one there is a cross leg robot, and this is a four legged robot. When
Cross-legged.
there is a no, the previous lessons 36 something cross
I
slider
are you talking about this?
diagonal legs.
Uh,
Uh,
this one.
no, yeah. See here, when the two legs are holding,
Yeah.
how the two legs are holding. If it is supposed in the air, there was a discussion with the air, some position. How it will hold that?
I didn't get your question.
No, there in this the four type of that we discussed that in above.
This one.
No. Top. Yeah. Here,
Yeah.
not here. Suppose here, it is leg one and leg two. If it is above in the some air,
Yes.
uh, how could be the other two legs are holding that robotic?
Oh, so this is a dynamic thing, right? So it will be moving with two legs at a time.
Yeah.
Rakshit has a something to say.
So it'll be alternate. It'll be moving alternately. I
Yeah.
think Sir has explained it.
It was lastly explained four, then
One,
two.
one for 2-3 arrangement.
Yeah.
Yes.
One,
So it will
So like
always maintain
this is
balance.
yeah exactly. You'll probably always have two legs on the ground.
always three legs in the
Oh
ground.
yeah, exactly. Yeah, so I had said yeah, always three legs on the ground. Yeah, yeah.
That's what my doubt. Whether the two legs was holding or three legs was holding.
Oh, even yeah, this is a really slow robot also. So because of that, it makes more sense. Like say, if you have three legs on the ground, you always have a stable. You can always make it stable. So
Yes.
you're just moving one leg at a time.
Yeah, can it
Yeah.
go up? It's there only. One slide up. It's there. Yeah, it's
Yeah.
there.
Uh,
Explaining the.
Yeah.
one, two, three. That means it is diagonally, and also it was showing the diagonal. So
Yeah.
one
So
minute. Uh,
the first leg one will be 1, 2, 3, 4, right? So your first move, you'll first move the top left and then the bottom right.
yeah.
Yeah, top right and then bottom left. Yeah.
Yeah.
Like this is also a very solid mechatronics project, but this is a little too expensive for most cases. You have to probably do this in in a workshop or college. Yeah. So with that, we kind of conclude the class of mechatronics. So next
Yeah.
week.
I have.
Hmm?
Yeah.
Okay.
Here,
Hmm?
here that spring that in the hardware complaint legs there is actuator. The spring was used here. Sir was told the spring was complaint legs. The portion the spring was used. Correct.
Yeah.
Yeah. Complaint link. There is a spring was used for that that more suspension and this one.
Yeah.
Yeah. Uh, whether like hydraulic or like air pressure pneumatic also, whether we can use.
I don't think so. Like I mean, the premise here is we want a legged robot, and we want a legged robot which is kind of like how humans and animals move.
Yeah.
So and essentially humans and animals kind of move by specifying the specific angles. So hydraulic and pneumatic motors are linear motors.
Yeah, see, in
So
automobile industry, my question is here. In automobile industry, whereas earlier we are using the suspensions for the spring, so and the same time in the hydraulic pneumatic also was that developed.
no, but wait. Firstly, actuators are very heavy, so I
Yeah.
wouldn't use that for these kind of applications.
Yes.
Like this is already incredibly slow. Moving at taking 3.3 seconds for moving forward. So hydraulic, I'm very skeptical of using that for in these applications. I do not think pneumatic can provide enough force also.
Mm. Yeah. Okay.
Like the for better or worse, what's that thing called? Electrical systems are just superior in a sense. Yeah. But yeah, that was a good question. You could kind of use a hydraulic.
Because
I guess after a if you cross a specific size, if you cross a specific size, then hydraulic would kind of make more sense. Like say you have a absolutely massive, like 18-legged robot or something. Then I guess you can use the hydraulic systems because that will look very cool.
what I'm here thinking that the mechanical the springers will be impacted on that of the time of the spring tension, maybe the environment property, the hydraulic like this, the smooth moving of that we can control on that pressure, the
That
suspension will be
that's
like we
true,
told that.
I guess.
Yeah.
Yeah, that's true. Yeah, I don't deny that. Yeah.
And also it may be if you selection of the fuel that viscosity of the fuel it can be controlled, that the force can be compared with the mechanical.
Yeah. Rakshit has a point.
So, are you planning to use hydraulics for this robot?
No, not for
Or
this
like,
robot. I'm saying that you, for a much larger robot, it
okay,
might be possible to use a hydraulic
use
system. Like
hydraulics, yeah, for this.
for a small quadruped robot, it's just not possible.
Yeah, this
Hydraulic robots are too heavy.
yeah, compliant links. This is only better. The spring
Yeah.
ones is the most ideal option.
Like
Thing called Boston Dynamics. I don't think they don't use hydraulics. Do they use
I
hydraulics?
don't think they use hydraulics either. Like no, hydraulics have a lot of like like secondly, because the hydraulic are linear actuators, you have to like design the system in a very specific way for it to work really well. So if you have your legs like this, well, you have one leg like that and the other leg like that, then you have to like place hydraulic systems like that, and yeah, it's doable, but
Chances of it breaking down is higher, and I don't think it will be
no, it's
stable.
not necessarily higher because, for example, if you look at cat cat by caterpillars, I mean the vehicles. Wait,
Yes.
bulldozers and the like.
Yeah, that one.
Those use hydraulic systems because they are big enough and slow enough that it's fine to use it for that. So, if I remember correctly, there was a YouTuber called Hacksmith Industries
Yes.
who
Yeah, they use
tried to
hydraulics.
make a massive hydraulic system with like a
Eight,
lot of
8
claws
of
and things
XP.
like that. But
Yeah,
if I remember correctly, it took a lot of effort, and it
it broke.
wasn't.
It broke down also.
Yeah, exactly. It's not an easy task.
Yes, both are you are very correct. It means to say whether that heavy weight and heavy load mass was there, where we can do that mechatronic like this system. There, the hydraulic will be in place of mechanical spring. The hydraulic will be can be used. Yes, that's correct.
Yeah, but it's just yeah, it'll be very difficult though. Yeah. So yeah, that yeah. Yeah, but no, so I'm usually just familiar with like small scale mechatronic systems. So I've not even used a pneumatic system personally, but it's doable, I guess. I've seen a person who has used a pneumatic system to make a controller itself, and that was fancy. Yeah. So yeah, so that kind of concludes the mechatronic classes. Next week, I will be taking a revision class of everything we have done so far. If there are any specific topics you want me to cover, I'll add it here. Like I personally felt like I could explain body plot a little better, but last week I just came. I was not really planning to explain body plots, in my opinion. So
Uh, in this lesson, in the last lesson 40,
yeah,
there is a planetary gear was used, but
yeah.
was not discussed more on that here.
Oh, so
Uh,
planetary gears. They
yes, in this,
probably you. I no. I'm not sure why they've used it, but planetary gears are just a very nice way for
yes,
like
if you see that
planetary gears
70,
have multiple technically has multiple inputs, and depending on the multiple inputs you can have you have a high level of controllability of the torques and angular velocities. So where is the planetary gear?
1738, slide number 1738, that Maxon planetary gears are used.
Slide number 17.
Uh, 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 yeah, seven, not seven, that session time 1738.
Oh, okay.
Uh,
No,
Maxon,
I remember seeing it also, but I don't know where it is.
eh,
I remember seeing another set of gears somewhere, but
yeah, it was discussed on that actuation system.
okay. Anyway, it is like yeah, as I said. So for this, the mechanics of the system is significantly more important than the okay. The coding is important, but the mechanics are also equally important. And to design this properly, you need to have slightly decent understanding of how to design mechanical systems, like knowing the what's that thing called, like finding the dynamics of each parts and all. So depending on the output of the motors, you might want to like gear ratio things. So sensors, controllers. Yeah, they probably use the gears for yeah, as I'm sorry if you're pronouncing your name wrong.
Yeah,
As
after this slide, it was discussed. Here you can see that. No, no. Yeah, top. I think
oh
plan.
oh, I guess they actually use it just for a gear ratio.
No, no, no. It was discussed here. Uh,
So if I'm honest, I have not seen those lectures.
no, no, no. It was there, like that forward, backward, that leg configuration. The no next to that. Yeah, after this, it was discussed the actuation system. After this formula, actuation system in this blow next to next to one or two slide, it was discussed.
Yeah, they've used a gearhead.
Yeah, it was told Maxon gearhead with GP442C. Yeah,
Yeah,
here.
yeah. So it's pretty intuitive, right? They've used it specifically for the reduction, or
Yeah,
probably they probably
230.
want this for the. Okay, never mind. Yeah. So I mean,
So here, this planetary here head, it will support all the individual, all the eight motor, or like
no, this is for an individual thing. Each of
okay.
the motors, each of the limbs have to be, each of the things have to be
Yes,
controlled individually. So
yes, yes.
like you'll have
So
one here, one here, one here, one here. Oh, you can't see my hand. uh,
yes,
you will have one here, one here, one here, and one here, and each of those will have an individual planetary gear. You're not having a central motor in the top, which is connected to each of them. You'll have like eight motors. You'll have totally eight motors for this system. Sarit also wanted to say something. You raised your hand a little earlier. Did he leave? Okay. So yeah, so that is. Okay, so as I was saying, if there's any specific questions you want me to cover for next week's class, I can cover it more. Uh, but I personally plan that next week we'll have a very quick revision of every topic. Like just like I have had the recap in the beginning of the thing, I will essentially take. Yeah, I'll just recap the entire course next week. So if there are any specific, like, I feel like I can like starting from here. Huh. I used to write my notes slightly better. uh, and then yeah, there. So I will basically look at all the notes and all the lectures and see if there are any specific topics that we want to cover. Yeah. So, are there any questions? So, if there are no questions, we'll kind of wind up. I will be here for another 15 minutes. Yeah.
So how much marks will be the exams for?
I do not know.
Okay.
I do not. I am not in contact with the prof, so I cannot say how the exam will be. I can ask my higher up and get back to you next week.
Okay, and any numericals or problems we should focus on?
I will ask and tell you. Wait.
Okay.
The sample project. Oh, are you talking about the the conveyor simulator. Since I didn't write the conveyor simulator, I actually spent too long trying to make this work, but it didn't work. I just made the conveyor break down many times. So, like some of the parts kind of made sense. PB start is probably the part which makes one of these things. Okay, so the conveyor on naturally makes the conveyor go. Cartoner on naturally makes the cartoner put things in. But so many things just didn't work out nice. But if I if I switch running on, you'd expect things to work nicely. So they have made an animation and all, but I spent so much time and nothing made sense. The one major issue I had is, why is the total parts not changing? This is just a counter. It should have changed. I'm sorry. This is not my code. I'm not sure. They have done a lot of weird design choices which I didn't understand. Like, and how did they make the sensors here relate to these animations here? So many questions, but I couldn't get it to work. Yeah, I'm sorry. I wasted a lot of time looking at this and trying to make it work, and eventually made the I made so many of these values trues and false in such a way that the thing stopped working. And then I decided I'll just give up. Yeah. Yeah. Like reading these makes me like whenever you write code, it is absolutely vital you write comments to your code. Otherwise, it's not just you. It's not. It's for everybody. Like the PLC type of coding does not make writing comments very easy. So maybe because of that, this is not that great. But yeah. Have almost no idea how they made the animation also. It's so well made, but why doesn't it work as it's supposed to? Okay, anyways. Okay. And yeah. Since I'm not a huge fan of awkward silences, I guess I'll talk a little more. So last week I kind of uh, flubbed through the oh, so regarding these, do note that the final value theorem, which comes in lecture in the the first controllers lecture. That's actually very important. That is limit E of that is, if you want to see the limiting, not limiting, like if you want to see how the limit of E as times tends to infinity, you can instead see this evaluate this limit. And for most what's that thing called, for most transfer systems, for most transfer functions, it's a much nicer problem to solve. So say you have say E of S is 1 by S into S plus 1, then E of T will be limit E steady state is limit S tends to 0 of S E of S, which will evaluate to be 1. How do I show this? Oh, we can. This is very easy to show. We can just take the inverse Laplace transform of this, and on doing the inverse Laplace transform of this, I think you'll get E of minus T. So this is, I think this is S plus 1. Yeah, this is 1 by S minus 1 by S plus 1. 1 by S is 1. That's super convenient. So inverse Laplace transform of this is 1 minus E of minus T. And if you take limit as T tends to 0 of this, T tends to infinity, this tends to 0, so the inverse Laplace transform is 1. If you want, I can explain this again. Essentially, the premise is this is important. And I just showed an example taking E of S is equal to this thing, and we can quickly see that they are indeed equal. Like, unfortunately now there's not enough time to explain more about body plots, but yeah. Okay, so I'll kind of keep. If there are any more questions, you can ask, and I'll try my best to answer. I'll be quiet now. So we can do simulations with the desktop version of MATLAB, but the computer I am using right now does not have the desktop version of MATLAB, and I don't think the online the application version of MATLAB has the same thing. This is an update. Wow. Yeah, so one very useful thing in MATLAB is Simulink, And with Simulink, you can properly do really good simulations. And there is no there. I don't think there is Simulink here. Yeah, we don't have Simulink in the Android version of the app. Oh, give me a second. Yeah. Yeah. And unfortunately, I can't even install MATLAB now because that's a 20 GB file. I can show it next week though, provided I get a license and all. But yeah. Okay, so it's becoming 7. I'll stop the recording now. If the I'll stay around for a few more minutes. So if you have any questions, I'll be feel free to ask. So yeah, thank you.